So I'd like to consider the following three series. First one is going to be the sum from n equals 2 to infinity of 1 over n squared. Second one is going to be the sum from n equals 2 to infinity of 1 over n squared minus 1. And the last one is going to be the sum from n equals 2 to infinity of 1 over n squared plus 1. All three of these series, we can determine the convergence or divergence of them using a variety of tests that we've already introduced. The first one would be considered a p-series, with p being equal to 2. Now, I guess the important part about that is that p is greater than 1, which lets us know that the first series converges. The second series that we have here would be considered a telescoping series. This is due to the fact that I could factor the denominator, n squared minus 1, into n plus 1 and n minus 1, then perform a partial fraction decomposition on it. For the last one of these, 1 over n squared plus 1, it would be relatively straightforward to perform an integral test on this one. Now, of the following three situations, you let me know which one sounds the most ideal. Oh look, p is 2, so the series converges. Alright, so we're going to factor the denominator, we're going to set up a partial fraction decomposition and verify that the last term goes to 0 to determine the convergence. Well, we're going to figure out that the function is positive and decreasing and continuous, and then we're going to do an improper integral from 2 to infinity of blah, blah, blah. It's my sincere hope that the first one was the ideal one in this situation. Now, the reason that I bring these up is they have very different ways of determining convergence, but you'll also notice that when n gets really, 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 really big, basically all of these denominators are going to be identical. Like, consider 10 million billion trillion. Now, this is 10 million billion trillion squared. This is 10 million billion trillion squared minus 1, and this is 10 million billion trillion squared plus 1. Essentially, the behavior is, once n starts getting really, really big, all three of these are acting basically the same. Now, the reason that I bring this up is because we're going to introduce the comparison tests. The comparison tests help you determine the convergence or divergence of a given series based off of comparing it to something else that you already know converges or diverges. So with that in mind, first one we're going to talk about is referred to as the direct comparison test. Now, the direct comparison test says, let's compare two series. And the series that we're going to compare are going to be the sum of a sub n and the sum of b sub n. Now, both of these are going to go to infinity, but the starting point doesn't particularly matter, which is why I'm not going to indicate what it is. I would like to suppose also that of the two series, that every a term is smaller than every b term. You are allowed to draw one of two conclusions. If the larger series is convergent, that means we actually get a sum out of it, then the smaller series is convergent as well. Suppose also that the smaller of the two series is divergent. Then that means that the larger of the two series is divergent as well. Now, all that we're saying is if the larger series is convergent, that means that we'll actually get a number out of it. It sums to, 8 or some number. Then this number, well, it'll wind up being smaller than 8, but more importantly, you actually get a number out of it, so that's important. If the smaller series is divergent, that means it tends off toward infinity, and that means that this series would be larger than infinity, so it will be divergent as well. Now, as it pertains to what we did up top, if we were to compare the sum from n equals 2 to infinity of 1 over n squared, and the sum from n equals 2 to infinity of 1 over n squared plus 1. The first thing to note is that the second series has a larger denominator, therefore it is going to be the smaller of the two series. Wait a sec. No, that's backwards. Screw it. New page. So we'll say note. Alright, so I'll write these two things down. Alright, so this one has the bigger denominator, so it's going to be smaller than this one. We're going to note also that the sum from n equals 2 to infinity of 1 over n squared converges by the p-series test. P is equal to 2, which is greater than 1, therefore it converges. Now that means that according to the direct comparison test, therefore, by the direct comparison test, the series n equals 2 to infinity of 1 over n squared plus 1 converges as well. So anytime you have a series that is smaller than a convergent series, that series will converge as well. However, let's consider the other two that we had up there. If we were to compare the sum from n equals 2 to infinity of 1 over n squared with the sum from n equals 2 to infinity of 1 over n squared minus 1. One thing to take note of is that if we were to compare these two, this one has a smaller denominator and therefore is larger. Therefore, by the by the direct comparison test, we draw no conclusion. According to the direct comparison test, we are able to draw no conclusion due to the fact that the only thing that we've shown is that this series would be greater than a convergent series. Greater than a convergent series could potentially converge, but it could also potentially diverge, as infinity tends to be bigger than things that are convergent. So because of that, we can draw no conclusion about this one, which means that we probably have to try something else. Well, the good news is there is something else to try.